So, okay, so let's recap what we did this morning. I hope I basically gave you some ideas about the basic concepts of nonlinear optics, especially as they relate to the development of OPO systems, OPO devices. We talked a little bit about materials, birefringent and quasi-phase-matched materials. And basically, also I gave you an idea how to build a generic OPO system, regardless of what time scale it's working, but some general, if you like, recipe to take home with you. If I want to build the OPO, I put my pen on the paper, what do I really try to do in the first instance? And if you remember, we looked at the equation for gain and how to maximize the gain in a single pass for the signal and idler that we generate. And that is always a very good recipe, and everything is included in that equation. Even for practical purposes of developing an OPO, you look at the equation for gain and try to maximize everything on the right-hand side of the equation. And in practice, it means to do phase matching, acceptance bandwidth calculations, avoid walk-off in order to maximize the length of the nonlinear crystal, and also use high-intensity laser sources, limited, of course, by the damage of the material. Now what I want to do in these 2 hours is now tell you really about real OPO devices in different time scales. So going from the generic concept that I explained to you now to a specific time scales. And I will go from femtosecond down to picosecond, a little bit of nanosecond, and finally CW, hopefully if there is enough time, and tell you a little bit of the applications of these systems. So let me, to do that, so I'm going to talk about devices now. Go back to our slide that hopefully we all like, and this famous equation here. And what I want to do is just tell you that, of course, when we do real practical OPO systems, we do phase matching. So our gain in signal amplification from here to here obeys this Cauchy squared gamma L equation. And of course, we can have this low gain regime, as I said to you, when we have CW lasers, and when we have very high intensity lasers, our signal amplifies very quickly in a single pass. Whereas we have CW lasers, our gain in a single pass is very low because we start from noise, and hence there is two different regimes here. So if we use that equation and do some very basic calculations, so let's say what I want to do, I want to work out this value of gain here in 4 different circumstances. For a typical nonlinear crystal, okay, oh, my table has actually moved. Something has moved here. Okay, it's a pity. They have to shift it that way. Okay, it's too late now. But what I am using here, so what I'm trying to do, I'm trying to quantify this Cauchy squared gamma L. So what is the signal amplification in a crystal that I use, let's say, KTP, with the effective nonlinear coefficient of 3 picometers per volt. I am pumping this crystal at around 1 microns, let's say with a YAG laser, okay, at 1 micron. And I'm running the OPO at degeneracy, so the signal and idler have the same wavelength. Both of them are around 2 microns. This is the refractive indices of the material. And so I can work out gamma from this equation here, okay? And I then choose my pump power, okay? And I decide to either use a CW laser, a Q-switch laser, a mode-locked laser, amplified laser. I don't know, in the notes, maybe this table has come out correctly. Has it come out correctly in the notes? Okay. So thankfully, I don't have to explain everything. But essentially, if I take a typical CW laser, again, I've forgotten, I think I use 5 watts, okay? And I use some typical values. So in this case, I use a crystal length of 10 millimeters. I use a spot size of 20 microns in my crystal, and I calculate the gain. I get something like 1.008. So the amplification of my signal from the input with a 5-watt laser focused to a 20 micron spot size in a 10 millimeter KTP crystal pumped at 1 micron, generating 2 microns, is, as you can see, 0.8% from what I started. And what I started from was noise, right? It was quantum noise, which is basically negligible. So over with a 5-watt laser with so much power, focusing to a crystal of 10 millimeters KTP, I have got negligible amplification. So if I put a power meter in my lab at the end of the crystal, I will not be able to detect anything because my amplification from noise is only 0.8% of what I put in, which is 0.8% increase in noise. Now, if I go to a Q-switch laser and I use a 10 millijoule, 10 nanosecond, corresponding to a 1 megawatt peak power, and I use 20 micron spot size. Sorry, I use a 1 millimeter spot size. Now, you might say, why are you using different spot sizes? Now, these are really practical parameters that are used in the lab because, as I said, for example, in nanosecond OPOs, damage is a major issue. So I cannot focus a high-energy 10 millijoule laser to a focus spot size of 20 micron in the crystal. It will damage. The crystal will blow up. So typical parameters that are used, I've put here. So it's a 1 millimeter spot size. This is the peak power per square centimeter of my pulsed laser beam that is in the crystal. Now I get a gamma RL of 0.77. And now I am increasing the signal intensity from the input of the crystal to the output of this 10 millimeter crystal by 70%. It's 1.72, 72% increase in the noise that I put in. Again, if I want to really make this device work in the lab, it's going to be very challenging because the amplification of the signal is very small. It's actually not like a laser. I mean, a laser, when you pump a laser material, you always get fluorescence, so you can even see it. But in parametric processes, it's very challenging because the gain is extremely low. As you can see here, we always start from noise. Now, if I go to another situation, I use a mode-locked laser, let's say a Ti-sapphire laser, and I have a 15 nanojoule, let's say a Ti-sapphire laser at 100 megahertz with 100 femtosecond pulses. I get 15 nanojoule pulses, 150 kilowatt. I focus it to a 15 micron spot size. This is the peak power of my laser in the crystal. Now, but what I do here, you notice I'm using a much shorter crystal. The reason I told you that you have temporal walk-off when you're using femtosecond pulses. So I can not use a 10 millimeter crystal that I did with a CW or Q switch. I can only use a 1 millimeter thick interaction length because of group velocity mismatch effects. And so these are just conventional or practical parameters. Now I've actually got a gain of about 1,400%. I have increased the signal intensity from noise from the input to the output of the crystal by a factor of 14, okay? Now, in the other, in the final thing, I'm actually using an amplified system. Let's say an amplified Ti-sapphire laser producing 100 femtosecond pulses, 200 microjoules, 2 gigawatts. And I'm, again, focusing the beam to 100 microns. Now, you notice I'm using 100 microns as opposed to that, because when you've got high energy pulses, again, you have to obviously be very careful with damage in the materials. And then now I'm getting a much higher peak power here in the crystal. Again, because it's 100 femtoseconds, I use short crystals. I go 35. This is the gamma RL. And then I get, now, look at this figure. So I'm actually increasing the gain in signal intensity from input to the output by a factor of something like 30. Now, you can see, even if you start from noise, a few femtowatts, you can calculate how much photons there is per mode in the vacuum. But even that, I can actually, 10 to the 30 is a really huge number. So I can actually, in a single pass, actually generate macroscopic output from this kind of device. So what I'm trying to say is that, again, because the table has been shifted, this column here corresponds to the situation where I have optical parametric generation and amplification. So many of you who probably work on very high intensity lasers, you have seen optical parametric generators and amplifiers. These are single pass systems that Benoit yesterday also put a slide to show you that if you have very high energies, and you can actually achieve very, very large gains. So in a single pass, you can generate sufficient signal and idler that are macroscopically amplified to be useful. Whereas in all other cases, in mode lock, Q switch, CW, your gains are very low. Look, from here to here, even if you increase the signal intensity by 14 times the noise, it's still noise, right? But here, no, this can actually turn to macroscopic output. So as a result, these devices here, CW, Q switch, mode lock, these are operated only, they can only be operated in practice as OPOs, not OPGs or OPAs. So you have to put mirrors around them in order to increase the gain by successive round trips in the cavity. So in the case when we have so in this column here, which is really this, we have very high gain, so our gain is very high. We have very high intensity laser sources. So in a single pass, I can generate signal on idler. I can put several different stages of these, and I can get an optical parametric generator or amplifier in a single pass, okay? This corresponds to very, very high gains. But in the case when my gain is low, which is the three first columns of that table, CW, nanosecond, and femtosecond oscillators at high repetition rate or picosecond, I'm in this low gain regime. And this is the variation of gain with the length and the gain factor. And in this case, I have to put mirrors around this cavity to make an optical parametric oscillator. Otherwise, you will not get a useful practical device. But the design criteria, pretty much at the fundamental level, are similar for both systems. You always want to maximize gain in reality. So this is, so of course, for this to happen, these are the sort of devices I will talk to you for the next hour and 45 minutes. I won't really talk about this optical parametric generators, because that has got its own field as well, and there is not enough time to talk about all of these things. So my focus is really on optical parametric oscillators. These are oscillators just like lasers. And of course, at the heart of all of these is materials. So these are some different materials that have been used over the years. These are quasi-phase-matched materials that Marty will tell you all about them, piplin, orientation pattern gallium arsenide. This is a very nice new material. I'll tell you about some of our latest results on that. This is an important material for the visible, and of course, this is a classical infrared material. But this list basically tells you all the different material parameters that have got to be satisfied to make a real practical optical parametric device, optical parametric oscillator, and or amplifier or generator. And as you remember, you need it to be non-centrosymmetric to exhibit chi2 nonlinearity. If you are doing birefringent phase matching, you need it to be optically anisotropic. But of course, you can overcome that if you use quasi-phase matching, and you can then do it also on isotropic crystals. Remember, I also told you that the material is, unlike a laser, there is no resonant interaction, so the material has got to be transparent at pump and parametric wavelengths. Ideally, you want to have as large an effective nonlinearity as possible. And these are, remember, we talked about all these angular acceptance bandwidths. There is also temperature acceptance bandwidths that I didn't tell you about. You want it to have low spatial walk-off. You want it to have high damage threshold, all of these things. So this is basically your wish list. I mean, ideally, you want all of these, but in reality, it involves a lot of compromises, making an OPO system. And depending on what time scale you're working, there is relative importance to these different material parameters. So, for example, if I work on CW, high effective nonlinearity is essential because I've got low intensities in CW regime. So I have to really be able to compensate for that by having materials that have very high nonlinearities. That is why before the advent of piplin, CW OPOs could not really be operated easily in singly-resonant. You need low spatial walk-off, very important, because with CW lasers, you have to focus to very, very tight spot sizes to get the intensity. As a result, double refraction and walk-off becomes a lot more important. So all of these things are here. So this is the different kind of CW, nanosecond, picosecond, and femtosecond. And of course, the red flags here are bad news in a way. The amber is okay. You know, these are desirable parameters, but they are not absolutely essential. But the reds are essential. And what you can see here, that if you operate want to make a CW OPO or a picosecond OPO, there is a lot more reds than, if you like, greens, okay? Whereas if you want to make a nanosecond OPO or a femtosecond OPO, there is more yellow and green. So these two regimes, they have advanced a lot more than these two regimes. In fact, it turns out to be the case. But, you know, I don't have time to go through all of these, but if you are interested, I can tell you why all these different relative. So these are relative material requirements. So you always have to be aware if you make an OPO in a particular time scale, what materials you really have to pay attention to. In nanosecond, as I said, damage threshold is very important. So this is essential. This is why the systems that Benoit explained to you yesterday with very large LBO crystals, or because LBO has got a very high damage threshold, or BBO. Whereas I think for CW, it is desirable, but it's not absolutely essential. Now, these are just some of the materials that have been developed over the years. In the early days that I think Benoit and I were probably sitting where you are sitting now, these materials were introduced, well, particularly BBO and LBO in the mid-1980s, early 90s. And because of their very high damage threshold, but remember, this is the effective nonlinearity. The effective nonlinearity of these materials is actually very low compared to quasi-phase-matched materials. But because they had very high damage threshold, you could make pulsed OPOs. So you could use high intensities to compensate for the low gain and for the low nonlinearity in these materials. And many pulsed OPO systems were developed during this period. And in fact, pulsed OPO technology is generally reliant on birefringent phase-matched materials. And this technology is very well established now. There is commercial systems from many companies. And of course, it was the advent of quasi-phase-matched nonlinear materials that opened up the door to CW, practical CW OPOs, because now you can use materials that don't have a very high nonlinear, well, they have much higher nonlinear coefficient than here, but importantly, you can also use very long interaction lengths through quasi-phase matching engineering. And as a result, you can actually make CW OPOs, and these materials are all you can do non-critical phase matching. You don't have to worry about walk-off and so on. So the advent of quasi-phase match materials now has made CW OPOs almost a standard thing for many labs. Right. And as I said to you again, the important thing about OPOs is their temporal versatility. And the reason for that is, as I said, the electronic susceptibility is almost an instantaneous effect as far as the optical radiation and light pulses are concerned. So because it's basically the gain is due to the dipole oscillations and dipole moment here, I can operate OPOs all the way from femtosecond to picosecond, nanosecond CW, whereas you cannot do that with conventional lasers because there is a gain storage associated with laser transitions, and you need very, very short upper state lifetime in order to be able to produce short pulses. So Ti-sapphire laser can produce very nice femtosecond pulses of few femtoseconds, few optical cycles, but neodymium YAG cannot do it because of fundamental limitations of how the laser works. Whereas with nonlinear optics, if I put a femtosecond pulse into this dipole, I can also extract the femtosecond pulse because the dipole responds instantaneously in time to any perturbations in time. If I put a picosecond, I can get picosecond, and of course, in principle, I can do it, but there is, as you will see, a lot of tricks are involved in order to get what you exactly want. So I want to now tell you a little bit about so this is hopefully you now get a perspective of if you are making nanosecond, CW, picosecond, femtosecond, what things you have to pay attention to. Now, I want to go from very short pulse systems, femtosecond, towards picosecond, a little bit of nanosecond, and ultimately CW, if I have time, and then tell you a little bit of applications. And the reason I'm doing it is because a lot of the recent advances in OPOs have been in these time scales. And Benoit already covered a lot of this stuff on nanosecond OPOs yesterday, and it was very interesting, as you noted. But I want to really go to the complementary side of it to talk to you about femtosecond OPOs to start with. So the reason, why do we want to make femtosecond OPOs? Again, as I said to you, the reason is the most established tunable ultrafast laser these days is the Ti-sapphire laser, and it has a limited tuning of about 700 nanometers just below to just above 1 micron. And what, of course, we want to do, we want to be able to generate femtosecond pulses in the other regions, okay? We want to go to longer wavelengths, shorter wavelengths if we can. And it has proved that lasers is very, very difficult, even with chromium, zinc selenide, and so on, although there is a lot of effort and a lot of success recently. There is some fiber work. There is some other things. But we want to see if we can use OPOs in order to do this. And, of course, as I said, one of the important features of nonlinear processes is that they're instantaneous. And that then has ramifications for how you can operate an OPO with a very, very short pulse pump laser. So when I put a very short, let's say I have a Ti-sapphire pump laser, I want to pump this OPO and generate a train of pulses at the output. The Ti-sapphire laser produces a very short pulse of, let's say, 100 femtoseconds. It comes into this crystal, it generates a signal. The signal and pump propagate, assuming that you have taken care of all these group velocity walk-off, temporal walk-off effects. It propagates through the crystal, and it gets amplified along the length of the crystal, goes here, comes back, and then, because gain is instantaneous, as I said to you, unlike a laser. In a laser, I can hit it with a pump pulse. The population can go to the upper state, and it can stay there for a while until the next pump pulse comes. If it's got a long upper state lifetime, it can actually, the population, there is a storage in the medium. With nonlinear optics, there isn't. So when the pump pulse has gone through, generated the first signal pulse, the signal bounces back, comes back to the input of the crystal, and now, in order to be amplified again, it needs to interact with another pump pulse in this train, the next one. And that is the only way it can get amplified, okay? Gain is only available when the pump pulse is there. So in order to make that happen, you have to make it to synchronous pump the OPO. What it means is that I put on my pump pulse train here, and then adjust the length of my cavity so that my signal goes around the cavity. By the time it comes back to the input of the crystal again, it coincides with the next pump pulse in the train. So in other words, the round trip time of my cavity has got to be equal to the period of this pulse repetition rate. And this is called synchronous pumping, okay? So in all of the femtosecond and picosecond OPOs, this is used. When you go to nanosecond OPOs, again, the gain is instantaneous, but because nanosecond pulses, you can typically use 10, 20 nanoseconds. You can make OPOs of 1 or 2 centimeters, a few centimeters, and the nanosecond pulse, over the duration of 10, 20 nanoseconds, you can have 50 to 100 round trips of the signal during the duration of the pump pulse, so you don't need to worry about synchronous pumping. But because now you're dealing with much shorter pulses, femtosecond and picosecond, you need to use this technique of synchronous pumping. So all the devices in the femto and pico that I tell you about are synchronously pumped. And you can get 2 different situations, but this is when you have a CW train of pulses. This is when you have an envelope as well to increase the energies. But all the devices I talked to you about are the CW, which is really the most useful configuration for these synchronously pumped OPOs. Right. So one of the most heroic experiments in this field is actually this experiment by Dan Edelstein. In fact, this is around the same time as we were probably doing our PhDs. And this was a heroic experiment that I am very glad I didn't have to do as a PhD student. But it was an inspiration for me because it was so difficult. So this is the first femtosecond OPO that was demonstrated. Now, how did they do it? Basically, this was a dye laser. In red here is a colliding pulse mode-like dye laser. In those days, they didn't have Ti-sapphire lasers. The Kerlens mode-like Ti-sapphire laser had not been discovered yet. So the only source of femtosecond pulses were dye lasers, colliding pulse mode-like dye lasers. So this is the green pump from an argon. This is a dye jet. So it's a jet with a liquid dye going through it. And then this red is the cavity. This is the saturable absorber. And this whole thing in red is the dye laser, getting very, very short pulses. However, the output from these dye lasers was very low, a few milliwatts at best. And we have just discussed that in order to see nonlinear effects, you need high intensities. So what they decided to do is, okay, outside the cavity of this dye laser, we have a few milliwatts. But if you put high reflecting mirrors inside, then we can have very high intensities inside the cavity, okay? And the pulses that are circulating, femtosecond pulses in the cavity, can have much higher intensity. So why don't we actually build the OPO inside the pump laser? Now, this is a very difficult experiment because firstly, you have to have this crystal is very thin. It's about 1 millimeter because it was femtosecond. You are also using non-collinear phase matching because you cannot have the same axis for the pump. This is the idler, and as you can see, the pump going in this direction through the crystal. This is the cavity of the laser, and non-collinear phase matching was achieved. And the signal, this was a singly-resonant oscillator. The signal of the OPO was resonated in this cavity. So the green is the OPO cavity, and then inside a dye laser cavity, and moreover, they have to be synchronous. They have to be synchronous. This is a synchronously pumped system. So it's synchronous, it's intracavity, and it's non-collinear. So you can imagine in the days that nobody had made femtosecond OPOs, this was a very difficult experiment. But anyway, it worked, and this really opened up the field of femtosecond OPOs, right? But of course, nobody, including myself, wanted to do this because this is too hard, right? And so thankfully, when we started thinking about this problem, then the Kerr lens mode like Ti-sapphire laser became available. And these are the sort of, then instead of a dye laser, now you could just use a Ti-sapphire laser, and you have sufficient intensity outside the laser to have your laser, and then you build your OPO outside the laser, which made life a lot easier. Still very challenging, but then people started using, again, a Kerr lens mode like Ti-sapphire laser. Very soon after, this is in 1992, about 2-3 years after. And again, this is the cavity of the OPO, and you use prisms here for dispersion compensations and so on. But this is the pump laser, and this is non-collinear phase match, and this is the OPO cavity. Now, recall that I said the OPO cavity length has got to be equal to the repetition period of the pump pulses, which means that the length of the OPO cavity has got to be matched to the length of the Ti-sapphire pump laser. So femtosecond OPOs actually turn out to be a lot bigger than nanosecond OPOs. They cannot be made compact. They can be, but the overall length of the cavity has got to match, although you can use harmonic pumping and so on. And these are other examples, including some of the things that we did. And this is a ring cavity, femtosecond OPO, and you use dispersion compensation. So in this case, you can remove the prism and just have a simple Z cavity, or you can put the dispersion compensation using prisms and then end up here with the cavity. And typically, these devices work over nanometers in terms of, if you like, a stable range of the cavity length. So you have PZT here in order to stabilize them, but also you can use this as a mechanism for tuning, as I will explain later. But so using the Ti-sapphire laser, many OPOs were actually developed. And because you can take a Ti-sapphire laser, it operates between 700 nanometers and 1 micron. You can pump an OPO, and as I said to you, OPO is a down conversion process, parametric process. So you always shift your fixed input pump wavelength to longer wavelengths, okay? So as a result, using the Ti-sapphire laser, Kerr lens mode like Ti-sapphire laser, so people really succeeded, many people, including ourselves, in actually using a variety of nonlinear materials, RTA, LBO, KTP, and using Ti-sapphire lasers of different pulse durations and rep rates to down convert and shift and cover these wavelengths in the infrared, which I showed you cannot fill with lasers, okay? Because the Ti-sapphire laser operates in this wavelength region, okay? And you're down converted to long wavelengths, okay? Now, but still, as of today, still challenges remain to go to longer wavelengths than about 5 microns. I will show you some recent results that we have actually gone to about 8 microns using some new materials. And also a challenge was also to go to shorter wavelengths, because as I said to you, and as Benoit yesterday said and Bob explained earlier, fundamentally the parametric process, which is the opposite of harmonic generation and some frequency mixing, is a down conversion process. So you can never generate output at frequencies higher than the pump or at wavelengths shorter than the pump, okay? So we set ourselves the challenge of, okay, how can we actually use nonlinear optics, frequency conversion, and OPOs, not only go to down convert to longer wavelengths, but also cover these gaps. And the reason for that is for about 20 years since the Kerr lens mode like Ti-sapphire was invented, it was difficult to actually cover the gaps below about 800 nanometers using below about 780 nanometers using any other means. So we set ourselves the task of trying to cover wavelengths shorter than the pump and beyond 5 microns, and these are some of the things that I'll show you. Sorry, this should be a micron, of course. I don't know. This is the fun problem. So the idea was, can we actually go to shorter wavelengths than the pump and also generate higher powers? So go into the visible. So this is a sort of timeline, historical timeline of what people tried to do, including ourselves, and what we finally managed to achieve to do. So this is what happened. Actually, I should really update this, but right, I haven't had time. But to give you a perspective, so this was the very first femtosecond OPO I showed you. That was Dan Edelstein with this intracavity with the colliding pulse mode like dye laser at around 600 nanometers. That was the dye laser, and he produced using KTP signal and idler wavelengths in this range using this very, very complex and challenging setup of intracavity pumping. This was the first femtosecond OPO. And of course, in 1991, the Kerr lens mode like Ti-sapphire laser was discovered, and it goes, let's say, it covers a tuning range from 700 to about 1,000. Yeah. And using this Kerr lens mode like Ti-sapphire laser, as I just showed you, a lot of people started to use these new materials that are also becoming available, such as rubidium titanyl arsenate and CTA, KTP, and so on. And then using this Ti-sapphire, again, down converting, covering these longer wavelengths here, as you can see, using this. And of course, a fantastic development was this, again, this landmark, which was the development of Piplin by Marty and his co-workers. And of course, that opened up the door to many, many more OPO, femtosecond OPOs being demonstrated using periodic pole materials, PPLN, PPKTP, and all kinds of different materials, using also fiber pump lasers. Now, again, as a down conversion process, this was expected, but what really revolutionized was the fact that now with Piplin and all these periodic pole materials, you could actually really almost, you know, it was becoming so much less challenging to develop femtosecond OPOs. The problem, of course, is if you wanted to go to shorter wavelengths, you could frequency double the Ti-sapphire laser. If I frequency double 700 to 1,000, I get 350 to 500. But it's very, very difficult to cover this 500 to 700 nanometer gap, generate femtosecond pulses. And this visible gap actually remained for nearly 20 years or more. And in the meantime, a lot of people, including ourselves, were trying to cover this gap somehow using non-collinear phase matching, using a variety of materials and critical, collinear, non-critical phase matching, and so on. And we had partial success in actually covering this wavelength range here. And until we managed to actually discover this new nonlinear material called BIBO, and using that and using a variety of frequency conversion steps in a femtosecond OPO, we actually managed to develop a device that with multi-step frequency conversion with a femtosecond OPO can cover all of this range. And we are actually also managed to go to shorter wavelengths using intracavity doubling of the femtosecond OPO. And this is a device that I will show you now in terms of its performance. But now you can see that with femtosecond OPOs, with a variety of material, you can now get wavelength coverage from the UV all the way to 5 microns, and actually beyond, as I will explain in a few slides in about an hour. In fact, we have now gone to about 8 microns using femtosecond OPOs with very practical powers. So the way we do this is we take a Ti-sapphire laser, and we frequency double it using external second harmonic generation. So this is our first nonlinear process. And then we use this, if you like, blue light, this second harmonic generated femtosecond pulses in the blue, to pump an OPO. And because now we are pumping in the blue, we can actually then generate signal wavelengths from 500 nanometers upwards. So even though we started with a Ti-sapphire laser at 800 nanometers, we are now making an OPO by frequency doubling and pumping it using these two nonlinear processes. And then we can also do internal doubling using a third nonlinear optical process to go into the UV using internal second harmonic generation of this, not external, but internal. And this, of course, the material that we actually used was BIBO, and this is BBO for going to the UV. So using this, we were actually able to generate from 250 to 2,500, limited by the transparency of the BIBO crystal. Of course, if there was another material like BIBO but was transparent to longer wavelengths, you could potentially go to longer wavelengths here. But you don't have to do that these days because you can use piplin with Ti-Sapphire. But this was actually a technique to go to shorter wavelengths. And the way we did it is using this very versatile nonlinear material called bismuth triborate, which is a biaxial monoclinic crystal, which has got very, very interesting phase matching properties for both. This is for type 1 second harmonic generation, type 2 second harmonic generation. And this turns out to be a very versatile material. You can phase match it in the 3 optical planes, and it has some very versatile properties. It's somewhere between KTP in terms of nonlinear coefficient and BBO in terms of the tuning characteristics, particularly in the YZ optical plane. So how do we do that in practice? Okay, so this is a gap-free femtosecond, visible femtosecond OPO. So we take a Kerr lens mode like Ti-Sapphire laser, as I told you. We use the first nonlinear process, which is the second harmonic generation in BIBO. We generate blue light. Then this is now our OPO system. Okay, it's a little bit different from the generic systems I showed you, but I'll explain. So we then focus the beam into a crystal of BIBO. Now notice this crystal is only 500 micron thick. And I explained to you when you're talking about femtosecond pulses, you have to use very, very short crystals because of temporal walk-off. This is the cavity of the OPO. The prisms are for dispersion compensation. But there is another fold in this cavity, and the reason for that is what we want to do. This is the signal that we oscillate in the cavity. One thing I probably should also mention to you is that in the parametric process, we have a pump. We generate a signal and idler. Now, you can choose to resonate either the signal or the idler, or both, or the pump, and as I will explain later. But in these kind of devices, these are called singly-resonant oscillators. So we only resonate the signal or the idler. In this case, the signal, because that's our visible light. We want the frequency doubling. And the idler is generated in a single pass through here with the pump. So what we do, basically, we have this resonant light in the visible, and we put another crystal of BBO with, again, a very thin 500 micron thickness, and then we internally frequency double the signal of the OPO as well into the UV. So we can get here visible, and here we can also get, out of here, we can get UV, okay? I won't go into details. In fact, the reason we use BBO for wavelengths below about 675 is that it has better proper nonlinear coefficient than BIBO. This is the characteristics of the BIBO. As you can see, you can phase match it in the YZ, XZ, and YZ plane again. It has some retracing behavior and some quite interesting phase matching properties. And so using this, we were able to, with the OPO, cover all of the range of 500 to 700 nanometers, in fact, from 480 to 710, using a pump at 415 nanometers, using type 1 phase matching with at phi equal 90 in the YZ plane of the crystal. So by rotating the crystal angle of the BIBO, we could tune this device. And this is some pictures of this device that once we got it working, it's a spectacular device because it's one of the few devices that you can actually see a resonant optical wave in the cavity that can tune so rapidly from blue all the way to green to yellow, orange, and red, finally. And my students always like to have their photos taken with them because and this is one of my postdocs who is looking. So it's not very often you can see orange light, I think, from a femtosecond system. And of course, for doubling, as I said, what we do, this is the second crystal of BBO that we use. So in the lab, you can see this is the dimensions of the system. The overall length of the OPO cavity has got to be the same as the pump laser, which in this case was 76 megahertz, which is about 2 meters, the overall cavity length. And this is the second crystal that is located at a different intracavity focus of this whole resonator. And with that, we can actually get ultraviolet generation. And this is the visible generation that's produced by the BIBO. You can do other techniques, again, all based on nonlinear optics, that you can go to the visible range. Another technique is, in the previous technique, we frequency doubled the pump. Then we took the the frequency double the pump, and then we pump the OPO to generate visible light. What you can also do is take the Ti-sapphire laser, pump an infrared OPO, take the near-infrared signal in the cavity, and frequency double that internally in another nonlinear process. And this is what is done here. Here, we directly take the Ti-sapphire laser, pump this OPO based on periodic pole lithium niobate, okay? So we get a resonant signal here in this wavelength range. The wavelength range, around 1.2 to 1.6, okay? And then what we do, instead of, we modify the cavity slightly here, and we put a second fold in the cavity, and then we put a BIBO crystal here. And the parameters of the BIBO in terms of the large acceptance bandwidth, and also for the piplin in this region, means that you could actually get very, very broad tuning, rapid tuning out of this device by simply changing the cavity length without even rotating the BBO crystal, because it has a very large acceptance bandwidth for second harmonic generation at these fundamental wavelengths. So you can generate very short pulses because of the acceptance bandwidth of the piplin is quite large, and at the same time you can get very rapid and broadband tuning in the visible. And okay, I don't know if you can see it, but this is the other version of the, if you like, going to the shorter wavelengths. So again, here you're using nonlinear optics, but using multi-step nonlinear frequency conversion processes to go to shorter wavelengths. Now, the graph I showed you, one challenge was to go to shorter wavelengths. Another challenge is really go to longer wavelengths, okay? And the reason for that is, as I think probably Marty will explain, and Benoit probably already explained, is that a lot of materials, especially the oxide materials that are used routinely for nonlinear frequency conversion, including periodic pole materials, they start absorbing around 4.5 microns, due to phonon absorption. So what we decided to do, this is a recent result. So what we decided to do, okay, if we want to use a Ti-sapphire laser, for example, and develop an OPO system, I showed you OPO systems have been developed up to about 4.5, 5 microns using these various materials. If we want to go to longer wavelengths, we have to use mid-infrared, classical mid-infrared materials. And a lot of these materials actually absorb at the wavelengths of this pump at 800 nanometers, even at 1 micron they absorb. So if we want to use widely available lasers to generate radiation beyond 4.5, 5 microns using the OPO process, it's very difficult. It's actually impossible. So what we decided to do, okay, we use another technique. And the technique to go to longer wavelengths is we are stuck with the pump lasers that we have. Ti-sapphire lasers, if we want to generate femtosecond pulses using this technique, we need to rely mostly on Ti-sapphire laser. So what we do, let's make an OPO first using a Ti-sapphire laser, let's say pump 1. It's synchronously pumped, and what we want to do, we want to pump it, okay, Ti-sapphire or another laser around 1 micron, but we want to go beyond 4 microns. We want to generate 4 to 12 microns out of this OPO. We cannot do it with a classical mid-infrared material because this will absorb the pump light. And nonlinear optics is basically a non-resonant. You cannot have absorption at the same time as a nonlinear response. So what we decided, okay, so if we make this OPO and then now use, out of this pump, we generate, let's use another conventional material an oxide material like periodic pole lithium niobate. And then with this pump, we generate a signal inside this cavity. Of course, we also generate an idler, but this is singly resonant, and from this pump, we take the signal and resonate in this OPO cavity. Now, because we have shifted the wavelength from the pump to a longer wavelength, we can shift it sufficiently that now it goes beyond the absorption edge of an infrared material that we want to use. So now we put another material here and we make another OPO, but now the second OPO, the second crystal based on the infrared material is pumped by the signal of the first OPO. So this is basically a signal resonant OPO, but we use the signal as the pump for the second OPO. Now, the advantage of this system is that not only you have shifted the wavelength can be tunable, and also because you're doing it intracavity, the intensities inside the cavity are much higher than outside, so you have a chance of getting the device above threshold. And so this is your your synchronously pumped OPO1, this is your synchronously pumped OPO2, and then by pumping the second OPO with the signal of the first OPO, I can generate a new signal, S2, and this is the idler from the first OPO that I may not use, but what I'm really interested in, this then can become the idler of the second OPO, and this is what we can actually generate. So the technique has got this sort of cascaded pumping. It has actually been demonstrated externally, as I will explain, but this is the first time that you're actually doing it internal to the OPO itself. And the advantages is that, of course, it reduces your pump power requirement because you're doing intracavity pumping. Again, the main reason is avoids short wavelength absorption in IR materials. And it is a composite cavity, so in terms of synchronization and stability is much, much improved compared to a cascaded series type of OPO. And it has flexible and broadband IR tuning because you can actually change this pump wavelength and change the output, or you can change the temperature. There's different methods because you can select this pump wavelength here by phase matching in the first crystal. And this is the color configuration of this type of OPO. And so what we have a Ti-sapphire laser. Our goal is to generate something beyond 4 microns, beyond 5 microns in the mid-IR. So we basically pump this OPO here. This is our OPO based on periodically pulled lithium niobate. This is an oxide material. Now, the signal that is generated here, okay, is now, instead of being at around 800 nanometers, it's at around 1.2 microns. So what we can now do is to put another crystal here. In this case, is cadmium silicon phosphide, CSP. And then we then split the cavities here. One, because as I said, these devices are synchronously pumped. So you cannot use the same cavity to resonate 2 different wavelengths. You will not find the condition unless under exceptional circumstances. And then you can run one of the cavities here, and you have and the other polarization through this cavity. And if you do that, then this is the sort of configuration which I've just explained. This is the CSP crystal that we got from Peter Schoenemann. This is the OPO working. And this is the characteristics of this beam splitter here, which are important. So it's high reflector for the signal of the Piplin OPO, and high transmission for the signal of the CSP. And in this way, we are able to make this OPO work. And this is the performance of this OPO. It still actually requires quite a bit of work in order to be able to robustly operate it. It's a complex system. We have to still improve quite a lot of the optics in this system. But essentially, you can tune the idler from about 5 to 8 microns here, as you can see here. And this is the output from the idler output in the mid-infrared. And as you can see, over about 2 hours, the peak-to-peak fluctuation is about 6%. So it's quite a stable OPO. And this is the signal wavelength tuning of the OPO, which is the signal of the cadmium silicon phosphide of this OPO. So this is one OPO pumped inside another OPO in order to extend this, tuning range. So in some ways, it's equivalent to what Dan Edelstein did, but now cascading 2 OPOs. But we are a bit lucky because we now have materials like Piplin and CSP, which are non-critically phase matched, and you don't have to do non-collinear pumping to get what you want. So this makes life a bit easier. Okay. Okay. Right, this is a very recent result. And thankfully, as I said, with the advances in materials, now we are able to generate go into the mid-infrared, beyond 4 microns, 4.5 microns. This is a recent result. And again, what has made this possible is the development of this new nonlinear material called CSP, cadmium silicon phosphide. And the guy who really is responsible for that is Peter Schunemann and Kevin Zawilski at BAE Systems. And this is a wonder material in some ways because you can pump it at around 1030 nanometers, around 1 micron. It's one of the very few materials that can actually be phase matched to generate and obviously have a low enough absorption to generate wavelengths beyond 5 microns. So this is the OPO, which is directly now pumped. We take a femtosecond ytterbium KGW laser, which is actually provided by the group of Harald Giesen. And these guys produce the material. And we make this OPO, as you can see here, with this 4-mirror OPO, CSP. It's a high-powered laser. It generates about 4 watts in about 300 to 400 femtoseconds at about 80 megahertz repetition rate. And using CSP, we can actually directly generate, we don't have to do cascading here. We can generate wavelengths from about 6 microns to 7 microns, as you can see here. This is the idler of the OPO. So we just take the laser, focus it into the crystal, and make this OPO. Again, remember, these are all synchronously pumped. Now, the way this device is tuned, because these are synchronously pumped, a very nice tuning mechanism in femtosecond OPOs is just through cavity length. I can adjust this cavity length, and I can tune this. I cannot do it in nanosecond, to a lesser extent in picosecond, and certainly not in CW. And the reason for that, actually, is you can think about it as it's due to the group velocity mismatch. I generate a signal in this cavity, which goes around this resonator with a certain group velocity. Now, if I change the cavity length slightly, it tries to find another wavelength within the phase matching bandwidth of the crystal that satisfies the new round trip time, because it's forced to do that. If you like, it's like, you know, we had spatial phase matching and we had our filter. This you can think about is a temporal phase matching, that the cavity length and the group velocity mismatch determines what wavelength is generated and satisfies the round trip time for the cavity optimally. So these wavelengths are totally generated by just changing one of the cavity lengths. Now, the great thing about this also is this will also remind you of what I discussed this morning about calculating acceptance bandwidth. So here we have a pump which is 2.3 nanometer in bandwidth, but calculating the acceptance bandwidth of this crystal, which is about 500 microns thick, the acceptance bandwidth is much larger than the bandwidth of the pump for that particular crystal length. As a result, we know that the interaction is going to be efficient. So this is the early calculations to make sure that the pump is usable, and this is all the results. And what is very nice is that this is a record power, we believe, that has ever been generated. 110 milliwatts we've actually generated at 7 microns in femtosecond pulses. You can see that the device is quite stable. This is measured over 1 hour. This is idler power stability at around 100 milliwatts. This is the signal. We can also extract signal through these mirrors. There is a bit of output coupling through these mirrors. And these are basically this is the signal pulse duration and spectrum at 1200 nanometers. This is the wavelength stability of the output in the infrared, as you can see here. And this is the frequency stability of the signal and idler, again, measured over about 15 minutes. And just to demonstrate that this system is actually useful, just a very quick measurement on toluene, looking at the absorption in toluene by just putting this femtosecond pulse on a microscope slide with some toluene on it and looking at the absorption and then comparing with the NIST database. There is quite a good agreement, as you can see here. So this is a sort of the combination of high-power femtosecond lasers at 1 micron with CSP now are able to directly take you towards these longer wavelengths beyond 5 microns at very practical powers, as you can see here. So now, this is going to longer wavelengths. Of course, I explained to you that OPOs are also very versatile because you can go to very, very short pulses as well. Temporally, you can go to few cycle pulses. Temporally, they're also very versatile. And as a result, what you can do, you can also go to very, very short pulses. This is an example of a device that we developed in collaboration with Max Planck Institute because they wanted a very broadband short pulse OPO for dual comb spectroscopy in the infrared. So you want to minimize the pulse duration, maximize the bandwidth of these pulses. And so we basically used the 20 femtosecond high sapphire laser, and we used periodically pulled lithium niobate with different grating periods with with total lengths as short as 250 microns to about 1 millimeter in order to actually test this system. And then this is a configuration of the OPO. We actually use chirp mirror pairs in order to maintain the pulse duration of the laser. And then we pump this OPO, as you can see here, in this cavity with or without dispersion compensation. And we spent a long time actually designing this OPO. It took a long time. But finally, this actually worked. And this is, as you can see, this device actually, firstly, it's very broadly tunable. It can generate very broad bandwidths because we are putting a broad bandwidth high sapphire laser and making sure that the acceptance bandwidth of the crystal can accommodate all of that pump bandwidth, which means we get efficient conversion, and then we can, on the other hand, get idler broadband output from this device. And this device, again, is tunable only by cavity length very easily. You can tune it from 2 microns to 4.5 microns. Broad bandwidths, I think this is full width half maximum bandwidths are around 450 nanometers. So I think if you take the sort of dB levels, they're much, much larger than that. And as you can see, yeah, about 420 is the bandwidth at around this wavelength here. And the device produces pulses as short as about, in fact, below 4.3 optical cycles. We have generated something like in the region of 3.7 recently. And you can see the device is also very stable. This is measured over 2.5 hours, and this is without actually locking. We only lock the repetition rate of the high sapphire laser without locking the OPO cavity itself, and you can see it's a stable system. And the frequency deviations in hertz, you can see here, are only about 1 millihertz as you can see here. And again, this is the variation of the interaction length and the idler bandwidth. And of course, as you go to longer, you can actually have longer pulses together with broader bandwidths and the other way around, and depending on the interaction length. For the interaction length as short as 250 microns, you can actually have broader idler bandwidths. And this is what we discussed this morning, because there is an inverse relationship between the crystal length that you can use and the bandwidth. And as long as you are within that bandwidth, then your interaction is going to be efficient. There are other very interesting things people have been doing with OPOs. I just finished this, and then you can have your break in about 2 minutes. This is from the Stanford group of Bob Bayer and Konstantin Vodopianov, who developed this very nice, interesting OPO. This is a femtosecond OPO, but now this is not a singly resonant oscillator. This is a doubly resonant oscillator. And if you run a doubly resonant femtosecond oscillator with type 1 phase matching, which means you have identical signal and idler waves at degeneracy, if you can arrive at the condition using the cavity length that the signal and idler, as I said, you can tune them. And then when they get to exact degeneracy, you can find a condition that one doesn't know which one is which. They're absolutely identical, so you get phase locking effects at degeneracy. And what happens as they get closer and as they're separate, the spectra are, as you can see here, separate. As you get them closer and closer, they somehow lock to each other in phase, and then you can get a very broadband spectrum here. And this is could be a first step towards making a comb, a stabilized comb. Of course, to get a real frequency comb, you need to stabilize this. But this is a passive comb, if you like. And using, again, interferometric measurements by mixing the signal, second harmonic signal, and the pump, you can actually say that actually the output is coherent, is phase locked, because you can see interference fringes. And this is the radio frequency spectrum. But when the two are not phase locked, you actually don't get any interference pattern, and you can see the satellite pulses in the RF spectrum. I think they also extended this to fiber pumping. This is a low rep rate, megahertz type of system, and using, again, chirp mirrors and so on, you can generate very broad band. But again, these are doubly resonant femtosecond OPOs at degeneracy. degenerate doubly resonant femtosecond OPOs. And this is another example going to longer wavelengths, and you get broadband spectra that then you can look at some absorption peaks. We also did something similar, but we like this material as BIBO because it turns out, very fortunately, that the group velocity dispersion and the acceptance bandwidth of this crystal, when you actually are looking for a wavelength at around 1.6 microns in the infrared, which means pumping at 800 nanometers, generating degenerate waves at 1600 nanometers. It has absolutely perfect properties for making a doubly resonant phase-locked OPO, which is what we did here using BIBO, and we get very similar results. And this is using a birefringent phase-matched crystal as opposed to piplin, which has been used, or opgas for all the other systems. Again, we see similar effects. You see the signal and idler, and then when you get to exact degeneracy, you can see that you get phase locking. And again, interference measurements, interferometric measurements also prove that this is a phase-locked OPO, and this is the characteristics of the OPO. For some reason, the thing in the middle here has not come out. It was a picture. But anyway, I think I will stop there and let you have a 5-minute break and then move on. OK, welcome back after that long break. I'm sure you're all really refreshed. You've had plenty of time to relax, so you could focus on the next hour. Right, so I've given you a perspective of femtosecond OPO technology. The next thing is going to slightly longer pulses, which is picoseconds. And again, there has been quite a lot of developments in this field over the last 10 and more years. And of course, with picosecond pulses, in some ways, the requirements on the pump laser is not as stringent because picosecond pulses can be generated by, for example, neodymium YAG or vanadate and other types of mode lock lasers. And not just Kerr lens mode locking, but other techniques are used. And as a result, these kind of lasers are very well developed. They can produce very high energies and also different rep rates. You can also frequency double them, triple them. And as a result, using these kind of lasers in combination with different types of nonlinear materials, you can actually develop picosecond OPOs. Again, these are high repetition rate, oscillator type systems running at repetition rates of 20 megahertz, but typically 80, 100 megahertz and above. So these are not optical parametric generators and amplifiers that are typically kilohertz or hertz, so these are oscillators. In fact, I should have probably, for some reason, I put an arrow here, but right. In any case, some things kept disappearing from my slides. But what I just want to emphasize that these devices now can really produce average powers of about 20 watts. In fact, above 20 watts using high power YAG lasers or vanadate lasers at 1064. And then when you go to obviously shorter wavelengths, the powers drop. But essentially, again, because we are down converting, we are pushing into the infrared, but then using the frequency doubled output or tripled output, you can also go to shorter wavelengths here, as you can see here. But going down below 600 nanometers is now also possible using various multi-step frequency conversion techniques. Now, what you also notice that there's a lot of materials that are used here, including LBO for wavelength generation using picosecond OPOs. And I put CW here because these are basically pulse train from these type of pump lasers are basically flat. These are continuous trains as opposed to a mode locked and Q switch type of lasers. And these devices, again, there have been some progress. These are very old systems that have been demonstrated, but really, in terms of for practical purposes, going beyond 5 microns has still remained quite difficult in this kind of systems. Again, because picosecond pulses are short, we have to do synchronous pumping with these devices. And so the typical lengths of these cavities are matched to the length of the pump laser. This is an example of a device we did several years ago. This is with my collaborators at the University of Mexico, and this could generate in those days with an Antares laser as the pump. Again, the pump has disappeared as well here as well, but this doesn't work without the pump. Just to emphasize, you definitely need to pump it. And in any case, you can actually generate, if you have the pump here, an Antares pump, about 20 watts. We managed to get 12.4 watts. This is the tuning of the device. This is piplin with type 0 phase matching, with different grating period. There was several different uniform grating periods. And you can see that you can tune this device from 1600 to 2,800 nanometers. This is the slope efficiencies, which can be as much as 74% here as a function of pump power here, going to about 18 watts. And this device really was developed because they wanted a system of high power and tunable around 1.85 because they wanted to do laser cooling, optical refrigeration in solids. And as I said to you, there aren't any lasers that can give you exactly the wavelength that you want. But as you can see with the OPO, we're able to tune that across this wavelength range corresponding to where the cooling in this material occurs. And this is an infrared image of the material. And when you actually get to the wavelength with the sufficiently high power and the sufficiently and correct wavelength, then you can actually see the cooling of the crystal here. And as you tune away in wavelength, then basically the optical refrigeration stops and the cooling stops. And this was basically, again, the OPO in a slightly different configuration. We have also taken these kind of devices to, now with new materials such as stoichiometric periodic lithium tantalate, again, you can develop picosecond OPOs. This is an example of another OPO that we developed recently. I won't go into all the details of that, but all I want to say, maybe explain to you that the powers that are attainable from these devices are typically in the region of a few watts. And they're very robust. They operate very robustly. This is over 12 hours and without any form of locking or anything. This is also sitting in the lab with any form of environmental protection. And okay, there is a drift here, but this is probably mechanical drift due to all the components of the OPO. This is the typical pulse duration that you can get out of these systems. This is an example of a cascaded OPO that I explained to you in the intracavity configuration. This is extra cavity configuration. And the reason, as I explained to you, if you want to go to longer wavelengths than 4 microns, you need to use materials such as ZGP. And of course, ZGP, you cannot really pump it at wavelength much below about 2.1, 2.2 microns, 2 microns. And of course, if you wanted to pump it directly at 1064, you cannot, obviously, this material will absorb, whereas obviously the piplin OPO and take the idler output about 3 watts to pump a second OPO. This is also a cascaded OPO, but in an external configuration. And of course, these are the results, as you can see, for the, okay, this is the idler output up to more than 3 watts here. I believe this is the, this is for the piplin, sorry. This is for the piplin, I believe. And this is the ZGP OPO wavelength. As you can see, it's tunable around 5.5 microns, and in the signal at around 3.5 to 4 microns. So these cascaded schemes are useful if you want to go to longer wavelengths. And these are some, I think, examples of the line narrowing of the OPO using some kind of diffraction grating. And this is the output signal power in the 4 micron range from this device, as you can see here, and the beam quality. Again, we have also made some experiments going to these longer wavelengths, and the thing that has made these experiments, again, possible is this new nonlinear material called CSP. And this is a very important nonlinear material, cadmium silicon phosphide. And this is a compact, this is a 450 megahertz OPO, still pumped with picosecond pulses. And so because it's a very high repetition rate, if you remember, I did say these are synchronously pumped. So the cavity length in this case is only 30 centimeters. And again, as I said to you this morning, in order to make sure that this OPO is going to work, you have to do calculations of phase matching bandwidth, because we know the phase matching, the spectrum of your pump, we know it's 0.16 nanometers. And then we also do the calculation of the parametric gain bandwidth. So we're basically calculating the spectral acceptance bandwidth for our crystal, which is 12.1 millimeters. And then we can see that our pump bandwidth is narrower than the acceptance bandwidth of our parametric process. So we expect to get efficient conversion of the OPO to work well. And this is a master oscillator power amplifier, which was provided to us by our collaborators and Antonio Agnesi and his colleagues at the University of Pavia. And this is a high-power laser. It's a mode-locked and Q-switch. This actually was for applications in biomedicine that we had a project to develop. These particular wavelengths in this region are very important for neurosurgery of the brain. It turns out that it can actually do neurosurgery with minimal collateral damage to healthy tissue if you use a wavelength around 6.4 microns, in fact. And so this is the OPO that basically, in some ways, it's a much simpler OPO than the other picosecond synchronously pumped, because we can actually design the cavity very simply by two mirrors, similar to the cartoons I showed you this morning with a crystal inside. But you have to make sure that the cavity length is exactly synchronized with the repetition rate of the laser, which is 450 megahertz. And this is the output of this laser. You can see the pump. When the OPO is running, the pump actually is eaten away or depleted, because the remainder of the pump is converted to the signal and idler output. So the pump depletion is always a good measure, as Benoit yesterday said, of the internal conversion efficiency of the system. Of course, you cannot extract all of that conversion out of the OPO, so the extraction efficiency is always lower than the pump depletion. But this is a measure of how efficient your parametric process is inherently, intrinsically. And the OPO could actually generate, as you can see here, outputs of the order of about 1.5 millijoules for 30 millijoule pump, and tunable over this kind of length. So typically greater than 1.1 millijoule over all of that range was produced by this OPO. And the drop in the output is that the transmission of this particular CSP sample, as you can see here, dropped. And as a result, the output also dropped in, following this drop in the transmission of the CSP crystal. This is the beam quality, and these are all the other parameters. You also get in many of these OPOs saturation of the output, in this case the conversion efficiency and pump depletion, and we find that in many cases it's due to thermal effects in these very high average power type of devices. Some other things that you can do in order to get to more for your money in the mid-infrared, in longer wavelengths, is to do things like photon recycling. So this is an example of such a system that was demonstrated by Karl Koch and Jean-Claude Diels and their co-workers. So let's say you have a picosecond, or it could be a femtosecond OPO, any kind. This is a generic approach. So you have a laser here, you pump your OPO. This is your OPO crystal. So, whoops. No, okay. So I have my pump, I generate my signal, and I also generate my idler. But what I'm really interested in is idler photons, because I want as much infrared as possible. So I really want to maximize the number of these photons at omega idler. I'm not that worried about the signal, because that's not of no use to me. I'm really interested in the idler. So what I do, I take the signal again, this signal, and I try through another difference frequency process, split this signal into two parts. Another idler, the same wavelength and frequency and energy as this, and another difference. So in effect, what happens between this and that, I end up with a pump, I get a difference frequency, and I get two idler photons. So for every pump photon now, instead of having one idler photon, I've recycled my signal, and now have two idler photons. So my quantum conversion efficiency, or my photon conversion efficiency, can actually be greater than 100%, as they have shown here. And the way you do it, you have taken, so this is the signal, so the pump is going here, this is the signal. You bring it back, so this the signal here. And then here, you do a difference frequency mixing process in order to then split that signal into a idler and a difference frequency here. And doing that, then you can see that in the case when you just have just the OPO idler, you have a power, as you can see, like this. And when you actually have that with the difference frequency mixing, the idler power, because you have twice as many photons now, is much, much higher. So this is kind of some kind of photon recycling that if you want to increase your infrared power, you can do that. OK, this is an example of, again, now going to shorter wavelengths. So we can do a similar thing that we did in femtosecond, in picosecond. So this is a 20 watt. This is now fiber lasers, because fiber lasers are now becoming very, very powerful. You can get picosecond pulses, very, very good stability out of these systems with good spectrum. So now you can push OPO technology towards fiber lasers, not just solid state lasers or YAG and so on, but now you can go towards fiber lasers. And this is an example of such a device. So this is pumped at 1064. This is PPSLT. And then we take the signal inside the cavity. We have another fold. And then we do another up conversion, intracavity up conversion in the form of second harmonic generation. So again, all of these are using nonlinear optical processes. And we frequency double it here. And then this is the performance of this kind of OPO. And you can see that we can generate visible light in the picosecond regime. OK, this one is 750 to 850, 860 nanometers. And this is the power in the signal. And this is the second harmonic power. So we can typically get watt-level output power in the visible spectrum tunable across this range. At the same time, we can also get idler power. So this device can produce signal, idler, and visible radiation at the same time. So spectrally very, very flexible systems. And this is basically the the pump depletion, and this is the idler power that you can see, 3 watts of idler power, around 2-3 watts of signal, and around, at around 2 to 3 watts of second harmonic of the signal in the visible, and up to about 6 watts of signal power. This all attainable from this kind of device. And you can see the stability of these systems over, this is 14 hours, and you can see they're very, very stable, even without any form of active stabilization. So these are robust systems now. Now you can go a step further now, and now also go towards generating ultraviolet radiation. And the way we do it, we take fiber laser, one nonlinear process. Now instead of directly pumping the OPO, we frequency double it first into the green. Then we make a visible picosecond OPO using MGO PPLT. And then now the signal in this cavity is in the visible, and then we frequency double it again, and then we can go to the UV. So again, using these multi-step frequency conversion processes, you can cover almost any wavelength range that you want with the sort of all these different nonlinear materials. And these are just, again, examples of this. And as you can see, the stability of these systems as well in the UV is about over 14 hours. Passive stability of 1.4% RMS. And this device is actually tunable from about 316 to 340 nanometers, entirely dependent on the grating period that we had available for the PPSLT. So there is no fundamental limitation why you can't access other wavelength regions in this. OK, I probably won't. OK, this is probably interesting to some people. Essentially, when we do signal parametric generation, you have your pump, you have your signal, and you have your idler that are generated. Now, these are through the energy conservation and phase matching, these quantities are locked to each other, right? So if I change, my pump is fixed. If I change my signal, my idler will automatically have to change in order to satisfy the energy conservation condition and be phase matched. Now, for some applications, for example, CARS microscopy, people actually want a specific combination of more than 2 wavelengths that are not necessarily matched to the energy conservation and phase matching in an OPO. So the basic motivation here was actually, can you come up with a modification to the operation of the OPO where you can actually generate more flexible wavelengths that can be arbitrarily tuned regardless of the energy conservation. So you can have a combination of pump signal and idler that wouldn't correspond to the energy conservation and phase matching, but would be able to be generated by the OPO. And of course, if we look at all the phase matching curves that you can get for all the different materials, this is like lithium niobate that I showed you. For every signal, for every idler, there is a signal. The same with BBO. This is typical phase matching curves. This is MGO to SPPLT because the signal and idler wavelengths are locked to each other through this conservation of energy and momentum. The same with Piplin. For every point here, there is another point here. So there is only a specific combination of wavelengths that is available, and only this kind of along a vertical line is allowed, if you like, spectral flexibility of the device. And you cannot go in other directions. If I want a wavelength here of the signal and idler here for a given pump, I cannot have it. So independent signal and idler tuning is not possible. The signal and idler are always tuned. Once you change one of them, the other one will change. And also, you cannot generally access degenerate wavelengths. There is all kinds of different problems involved there. So the idea here is now use two crystal configuration. So what we do, we can basically take an OPO and take a pump laser and make a cavity, as you can see here in the red. On one side, we can put one Piplin crystal, and the other one, we can put another crystal. This is a dual wavelength OPO in the sense that we can pump this Piplin 1, as you can see with this pump from here. It runs in this direction. We can pump this one in the other direction. And because they're propagating in opposite directions in the respective crystals, they don't interfere. They don't see gain because they are, okay, there might be some backward parametric generation, but we don't see it. And we basically can then, in a single cavity, we can actually tune these two crystals independently, and as a result, be able to get any combination of wavelengths across the phase matching range that we want. So you can change the temperature of, keep one of them fixed, one of the temperatures fixed at 50 degrees C here, for example, and change the other temperature, and you can tune that wavelength and keep that one fixed. Or you can have any combination of wavelengths, including degeneracy. We can actually go to exact degeneracy in these without actually having any interference between the two resonant signals. And it turns out that the operation of the both OPOs, if you like, in a single cavity is very, very similar. And you can get very similar pulse durations. There is some differences, and that is due to the fact that one of the crystals is slightly different from the other one in length, and also the oven designs are slightly different. So there are some differences, but overall, you can get this dual wavelength operation and with very good stability over hours, as you can see here. Again, and this is the beam quality, and this is the output power in the case of the one of them. And what you can also do, by actually changing the delay line here, you can also, if you like, play with in time, play with the pulses that are actually emitted from this OPO, basically in time, that you can actually do some kind of any kind of delay that you might require between the pulses, you can actually achieve by playing around with this delay. If you have a delay line, you can actually do that. Now, this is the latest result that has just been achieved, and this has not yet been presented, but because Benoit, my good friend and collaborator, gave us this very nice crystal, this is a cylindrically cut OPO crystal using uniform grating, but using a cylindrical phase matching. And the nice thing about this system is that you can achieve very broad tuning with a uniform grating and at a fixed temperature through just angular rotation of this crystal. And this is what we have just achieved. These are the results in the last week, essentially. And this is a picosecond fiber laser. This is the periodic pole lithium niobate crystal that was grown by Takanori Taira and fabricated by him. And then Benoit has, and I think his colleagues have actually made this cylindrical, if you like, facets of this crystal, and we rotate this crystal, along the axis perpendicular to the plane of the paper, and this is the OPO. And as you can see, by rotating the crystal, this is the angle relative to the incident pump beam, you can actually get broad tunability all the way from 1.5 to about 4.2 microns. This is the stability of the device. Again, over 15 hours, it's nice and stable. This is the wavelength stability. This is the power stability. And we don't, at the moment, have a very optimal output coupler. So the output coupling is at the moment only about 10%, and we can see the power actually rises around here when the output coupling here is around 10% or below. It's lower power. And when we don't have an output coupling, we are just in this singly resonant oscillator regime. We have about a few hundred milliwatts. And this is the idler output. And we know that for sure, still, by increasing the output coupling, we should be able to generate several watts out of this system. So this is also quite interesting because it allows you to also rapidly tune these devices, not just because the temperature tuning is slow. Another, of course, technique would be instead of a cylindrical crystal, use a fanned crystal. But of course, making fan grating structures, unless you're Marty or some other expert, it's quite challenging, especially over long interaction lengths and wide apertures. So using this kind of uniform grating with cylindrical phase matching can be a very nice solution for rapidly tunable systems, which, okay. Half an hour, I hope to tell you now about CW OPO. So we've gone from femtosecond to picosecond, and now CW. Okay, CW OPOs. Right. In CW OPOs, I will tell you a little bit more about resonant configurations because it's much more important. In the picosecond, femtosecond, and nanosecond, I did tell you that we generate a signal in idler. We resonate one of them. These are singly resonant oscillators. It turns out that the threshold for singly resonant oscillators is much, much higher than if you decided to resonate both waves, or if you decided to resonate signal, idler, and pump. But because we have high intensities in the nanosecond, picosecond, and femtosecond, higher intensities, we can operate these devices as singly resonant oscillators. But when you go to CW OPOs, you need to take a lot more care because you don't have a lot of intensity. And if you remember the table I showed you of all the material requirements, there was a lot of reds in that column. So you have to be quite careful how to actually make these systems work. And a singly resonant oscillator is, I have the pump, I generate the signal and idler, but I only resonate one of them, let's say the signal, and I let the idler pass through. I can also make a pump enhanced singly resonant oscillator where I also resonate the pump in the cavity as well as one of the waves, the signal, say, and then also let the idler basically go through. I can make a doubly resonant oscillator where the pump is basically single pass, just like singly resonant, but I am resonating both the signal and idler. This is called the doubly resonant OPO, and I can go to the extreme, which is resonate all the waves, so there's pump, signal, and idler. This is a triply resonant oscillator. Okay. The only example I gave you of a doubly resonant was when we had a doubly resonant femtosecond OPO that we had phase locking, if you remember, for this comb generation. But all the other devices I've talked about are singly resonant oscillators. And of course, generally, they have high thresholds, but because we have high intensities in the regimes I already talked to you about, you can operate them as singly resonant oscillators. On the positive side, they're very, very useful practical systems. If you now go in that direction towards triply resonant oscillators, then you have much lower thresholds. And now also, if you make these devices, stabilize them, they can be very, very frequency selective because this device will only be on resonance when all three optical waves can be held on resonance in that cavity. As a result, these devices are very good for frequency selection if you want to generate very, very pure stabilized frequencies with active stabilization because the resonance conditions are quite constrained. These are over-constrained devices, and they have low thresholds. On the other hand, these have quite complex tuning mechanisms. The protocols are complex, whereas if you go to singly resonant oscillators, a singly resonant oscillator, as I will explain, is pretty much like a laser as far as the tuning is concerned, and it can also produce extremely high powers. As I showed you, all the things that we have seen so far, you can generate watt-level output powers, whereas these devices here, they generally have complex tuning mechanisms, and the powers that you can generate from them are typically much lower. So these are more, if you like, in tune. If you don't have a lot of pump power and you want to make a CW OPO, you have to resonate more and more of the optical fields in the cavity. So, okay, this is another type of, I won't go into that, but into detail. But if you want to make a singly resonant oscillator and you don't have enough pump power, you can put the OPO inside the pump laser itself. And this is called an intracavity singly resonant oscillator, where I basically have my pump. Initially, I have my pump. Inside the cavity, I use a high finesse cavity, and then I put my OPO inside. Because inside this cavity, the pump power is much, much higher than the outside. Then I can make this OPO work. Now, it turns out that the steady state threshold for a singly resonant oscillator, just to give you a perspective of what is involved, if I have a singly resonant oscillator, want to make a singly resonant oscillator typically, or a doubly resonant, what is the difference in the amount of pump power I need in order to make this device work? So if I have a singly resonant oscillator here, and again, from the equation for gain, the gamma squared, L squared, that was my gain in a single pass of my crystal. If I equate that to the total round-trip loss of my cavity, okay, a singly resonant oscillator, remember what, again, going back to the coupled wave equation, solving them, finding the equation for gain, gamma squared, L squared, because we are in the low gain regime, if you remember. Gamma L is smaller than 1. And it's a singly resonant oscillator, so my signal is resonated in the cavity, but my idler has got 100% loss. And if I then equate this equation here, I do an equivalent calculation for a doubly resonant oscillator now. Now the doubly resonant oscillator has got the same signal loss, but now the idler loss is also very, very low. 100% reflectivity for both signal and idler. So I've actually made both of these waves resonate in the cavity, and then I basically calculate this is the threshold equation, and then if I divide one by the other one, what I find is that the threshold of a singly resonant oscillator over the threshold of a doubly resonant oscillator with the same loss of the signal, but an idler loss of alpha I, okay, is given by 4 over alpha I, okay, where alpha I is the loss of the idler in the doubly resonant oscillator. I can do a quick calculation, an example of calculation. So I take KTP, 10 millimeters. This is the same calculation I did for gain, if you remember. And a pump at 1064, according to the table I showed you before, I use a spot size of 20 microns, a beam width of 20 microns. I'm pumping at 1064 with a 10 millimeter KTP crystal, and I have a loss of 2% for the signal. In practice, you cannot obviously have a loss around much better than this, typically with the mirrors and cavities and so on. I calculate a threshold of 14.4 watts. So this is a CW OPO. If I want to make a singly resonant oscillator with a KTP crystal of 10 millimeters, focusing the beam at 1064 nanometers to a spot size of 20 microns in this crystal, I need about 14.4 watts of pump power just to make this device work. Now, if I make a doubly resonant oscillator, and now I just have about I make also the idler resonant as well as the signal in the cavity, do the same calculation, I get a threshold of about 72 milliwatts. So you immediately see that the difference between resonating both or resonating one is absolutely huge. So one is typically about 200 times the other one, okay? So this gives you a perspective of if you want to develop CW OPOs, depending on what your priority is. You might want to develop a singly-resonant oscillator if you want high output powers, but that requires high power pump lasers. If you want frequency selection and fine-tuning, but you don't have a very high power pump laser, then you might want to consider doubly resonant oscillators. And of course, the pump enhanced and other ones are somewhere in between these. So this is the doubly resonant oscillator, and so it has a low threshold, as I've just shown you, can be tens of milliwatts. It's very frequency selective, but in order to operate these devices, you generally need single frequency pump. They have complex tuning mechanisms. You need pump frequency control, and you need cavity length control. So these are typically actively stabilized OPO systems, okay, doubly resonant oscillators. Now, the reason for that is, okay, trying to illustrate that here if I can. So what we have, you recall, we have the parametric process, and we have a gain bandwidth here. We have a gain line shape for our parametric process. If you remember, we defined this bandwidth between delta k equals minus pi, and delta kl was minus pi and plus pi. So this is the bandwidth is 2 pi over L. Now, so this is where I can actually find gain. If I pump my OPO over this bandwidth, I will have gain. I want to operate my OPO somewhere within this bandwidth. Now, I have a doubly resonant oscillator. I'm resonating the signal, and I'm resonating the idler. If I want to resonate both of them, they both have to be an axial mode of my oscillator, my laser, right? I mean, I have to have, you know, the free spectral range of a cavity is defined by the separation of these modes. So because I have the signal, I have a set of frequencies here that could be the resonances of my cavity. I have a set of idler resonances as well, okay? They have to satisfy these conditions. For them, in order to oscillate in the cavity, they have to be a resonance mode of the cavity. They also have to satisfy energy conservation. This is, of course, my phase matching. The phase matching is much broader. The energy conservation is much more restricted. And of course, if you like, this is the frequencies of the signal increasing that way. And of course, this is the frequency of the idler. Of course, if I turn this axis like this, okay, the idler also goes in that direction. But the idler frequencies are here, because the idler is always lower frequencies than the signal. But essentially, if you take the, if you take the degeneracy point and then fold the axis on itself, it's easier to see everything. So then the frequencies of the idler are going in that direction, okay, increasing the signal in that direction. Now, the problem is we have dispersion in the cavity, okay? As you go to the different frequencies here are going to experience different dispersions in the cavity. And as a result, the intermode spacing here is going to be different from here. So, and of course, because you have to satisfy energy conservation, anything that would oscillate will have to be equidistant in frequency space from this degenerate point, which means that because this spacing here is all the time changing and this spacing is all the time changing, it may only be possible to find one frequency pair, a signal and an idler, that actually coincide. In order for them to satisfy energy conservation, they have to coincide on the vertical line here. And at the same time, they have to be a mode of the cavity through here. So this is going to be the operating point of your device, okay? So if you make a doubly resonant oscillator, and you have to lock it in order for it to stay on this single mode pair operation. If you don't, what you will find, any small perturbations in the cavity is going to make these two axial mode spectra to actually move relative to each other. So if you make a doubly resonant oscillator and don't make any precautions to lock it, what you'll see at the output is huge fluctuations in output power and also frequency, okay? Because the system basically is all the time, these two picket meshes are actually moving all the time. So this system is actually over-constrained, okay? And if you want to tune such a system, what do you do? So normally these kind of OPOs, because you get frequency selection and very narrow line width, people want to use this for spectroscopy. So what they want to do is actually tune the frequency across a molecular transition or atomic transition. So you need to be able to smoothly tune these spectra. So this is called fine tuning. And so how do you do it? Okay, so I have a pump here. I have to satisfy energy conservation condition, okay? Let's say if I have a fixed frequency pump, okay, what I can do, if I want to satisfy this condition, if I have a fixed frequency pump here, the only way I can satisfy this condition and still maintain resonance is if I increase the signal frequency. At the same time, I have to decrease the idler frequency so that this equation is actually satisfied, right? If I have a single cavity, for example, and I try to change these frequencies, okay? With a single cavity, I have a fixed pump laser, and I pull this cavity, the signal frequency is going to lower, but the idler frequency is also going to lower. So on the right-hand side of the equation, things are going down. On the left-hand side, things are fixed because my pump is fixed. So the OPO is going to switch off. I cannot satisfy energy conservation condition. So how do I actually tune such a device? Okay, there is two ways of doing it. One, if I have a single cavity, I can actually tune it by pulling this mirror. But in that case, my signal and idler, if you like, as I'm stretching this cavity, the wavelengths are getting longer, the frequencies are getting lower, and as a result, this side is going down. Now, if I have a pump whose frequency I can change to keep up with the change in the frequency on the right-hand side, so I have a tunable pump, if you like, then I can, as this goes down, as I pull the cavity, I can actually also reduce this frequency. So I can do a single cavity tunable doubly resonant oscillator. So I have some kind of a lock. As I lock my pump to the cavity length here using electronic stabilization. As I pull this cavity, I then also make sure that the pump actually tunes accordingly, and I keep this frequency energy conservation condition. Now, in many cases, I don't have a tunable pump. I may have a fixed frequency pump, which is quite often the case with single frequency lasers. If I have that, then what I can do then, in this equation, if this is fixed and I want to tune these, finely tune the signal and idler, if I tune this one down the way, I can tune that one up the way. But if I want to do that, I need to have two separate cavities. Increase the length of one and reduce the length of the other one, okay? And then I have a beam splitter, and I make one of them. If this is fixed, as I tune one of them this way, decrease the signal frequency here. In this one, I increase the idler frequency, and I can still find the energy conservation condition. So the tuning protocols for these are quite complex, but this has been done again. These are some results from many years ago now. People have done these things, including at St. Andrews. This is a fixed frequency. So this is a fixed frequency YILF laser. This is a tunable laser with a single cavity. And then you can actually get fine tuning. And every time you go through a free spectral range, you get mode hops. But you can get smooth tuning of these devices. And these have been used to do, for example, a spectroscopy. So as you tune the signal and idler finely across an atomic transition, then you can actually see the profile. So smooth tuning is very important in these devices for spectroscopic applications. This is another example using a diode laser. Again, because it's tunable, you can use a single cavity OPO and still get tuning. And this is also using some spectroscopy. This is an absorption experiment. This was done at Aculite. And you can see that you can get 40 gigahertz continuous tuning. So here we are dealing not just with the broadband tuning of the OPOs, but we are also dealing with very, very fine tuning for spectroscopic applications for this type of OPOs. And you're talking about gigahertz continuous tuning and small line widths. Now, the singly-resonant oscillator, on the other hand, if you might want to make CW singly-resonant oscillators, so you only resonate one of the optical waves, you can get high power and efficiency, multi-mode pump with single tuning. But as I said, as the calculation showed us that the threshold for these devices can be very, very high. In KTP, it was around 14 watts. Thankfully, because of Marty and other people who have developed the periodically pulled materials, now you can actually make the threshold of singly resonant oscillators of the order of a few watts. So these devices are now much more prevalent than they used to be 15, 20 years ago. But the great thing about singly resonant oscillators is it's just like a laser in terms of tuning mechanism. And the same thing as we had for the doubly resonant oscillator. Now, because the idler is not resonant in the cavity, it doesn't have to be an axial mode of your resonator. It doesn't have to form a mode spectrum of the resonator, so it's free. So the signal spectrum, basically the signal will have a spectrum which corresponds to the the resonance that it can find, and it will always find the resonance closest to the gain, peak of the gain here. And because there is no resonant frequency here, you only have one resonance condition. And because this is fixed by the cavity, your pump is fixed, the idler will automatically adjust it itself because it's much, much narrower than the gain bandwidth of your system. So it will also find a frequency that automatically satisfies the energy conservation condition. So this is in terms of if you want a high power system with almost all the characteristics of a laser in terms of power, tuning. It's not very complex in terms of tuning mechanism. And you can also achieve single frequency operation in these devices, as I will show you, by using, for example, etalons in the cavity, as you do in lasers, frequency selection elements. But you don't have to worry about so much about these complex tuning protocols as you need to do with doubly resonant oscillators. So this is much more unconstrained, and it can give you higher powers, but it has higher threshold. And this is just some of the examples I wanted to show you, just to show you the impact of periodic pulled lithium niobate and other quasi-phase-matched crystals on the technology of CW OPOs. Because before the advent of Piplin, people were trying to make CW singly resonant oscillators in the early days with these materials around here, RTA, KTA, KTP. Now, this is a plot of the threshold for the OPO with different resonance configurations, assuming all the other parameters are the same, crystal length and so on and so forth. So this is pump enhanced, this is doubly resonant, triply resonant, this is a singly resonant oscillator. So if we wanted to, for example, make a singly resonant oscillator using KTP, as I showed you with the calculation earlier, the threshold of this system, if we wanted to make a singly resonant oscillator, could have been as high as about 10 watts. And of course, there isn't that many people who have 10 watt CW lasers, or in those days, certainly it was much more difficult. And so a lot of people basically made doubly resonant oscillators with thresholds somewhere in this region, around 100 milliwatts to a few hundred milliwatts, as you can see here. Or triply resonant oscillators have even got much, much lower thresholds of a few milliwatts. But again, more complex tuning. But then singly resonant was very challenging until, of course, Piplin came along with the D effective of 15 to 16. And suddenly, if you look at this SRO curve, you'll see that the threshold for a singly resonant oscillator with an equivalent length of Piplin suddenly has come from 10 watts down to about 1 watt. So suddenly, people were able to make singly resonant CW OPOs using periodic pulled materials like Piplin, and now these are some of the workhorses of a lot of spectroscopic applications. Now, just to demonstrate one of these early devices, the first attempts to make singly resonant oscillators here using this KTP crystal was done in 1993, actually. It's time flies, actually. It's amazing. But this was done in the group of Bob Beyer at Stanford, and this was so they use a KTP crystal here to make a singly resonant CW OPO. They had a single frequency injection lock YAG laser. They did second harmonic generation using resonant doubling, and then basically tried to pump this OPO here. Okay, the OPO is essentially, okay, this prism is really used to separate the idler, but this is the OPO in this cavity here. But the problem was, as I showed you, the threshold for a singly resonant OPO with the KTP crystal is of the order of 14 watts, something like that. So what they tried to do, basically Bjorkholm, many years before that, showed that if you have a situation where you double pass the pump and idler through the OPO, so they put an extra pump mirror here to double pass the pump back into the crystal, and at the same time, also double pass the idler using this mirror. So the pump and the idler, normally in a singly resonant oscillator, are basically extracted in a single pass. But because the OPO could not be operated as a singly resonant oscillator, it had a very high threshold. By double passing the pump and the idler, you can actually get a threshold reduction of by a factor of 4. So if, let's say, we had 14 watts, divide that by 4 is of the order of 3.5 watts. You could actually make this device work. But of course, because now on the double pass, you've got the pump, you've got the signal, and you've got the idler. According to what Benoit told you yesterday, the phases are very, very important in going through for nonlinear processes. And because in the double pass through the crystal, if it was a pure singly resonant oscillator, basically, you wouldn't worry about the phase of the returning signal because there's no pump and there is no idler. But if you now are passing the pump, idler, and the signal back through the crystal, you have to make sure that the phases are actually correct and correspond to this phi1, phi3 minus phi2 minus phi1 minus pi by 2 in order to be able to operate the OPO. And it turns out that this actually shows, as you move the pump mirror and change the relative phase of the pump and signal and idler on the return pass, you can actually get a reduction factor in the threshold by as much as 4. And in this way, by double passing the pump and so on, they were able to actually make this device work. But it only worked when the correct phase relationship between the pump signal and idler on the return pass through the crystal was maintained. In other words, at 0 pi, 2 pi, 4 pi, 6 pi. So this device basically operated only when the position of the mirror corresponding to the correct phase. And this is basically, this mirror basically defines this phase here. Now, so they made the first singly resonant oscillator, but you would agree that to make such a device work, you have to stabilize the pump mirror and one of the other mirrors. So it was a very nice demonstration, but really the practical development of CW SROs was when actually Piplin became available. And this is the paper by Walt Bosenberg, who at the time was at Light Wave Technology. I think Marty is on this paper as well, I think. Yeah, I think so. That's right, yeah. Yeah, light wave electronics, and I think this Piplin was I think, fabricated I think in Marty's lab or somewhere around there. And for the first time now, you were able to actually pump singly resonant oscillators. You didn't have to double pass the pump or the idler, and the thresholds were now not 14 watts, but the thresholds were of the order of 4 watts, as you can see here. This is a ring cavity. This is the threshold for the linear cavity and standing wave cavity of 6 watts. And this is the idler wavelengths that you generate from this device. And as you can see, for the first time now, you can make singly resonant oscillators with low threshold of 4 to 6 watts, but high output powers. You're talking about 3.5 watts of output power, 4 watts of output power for about 8.5 watts of pump and tuning. So you have now made an equivalent of a laser using a fixed frequency laser. You have made another laser with very high power, very broad tuning, and behaves also like a laser. You don't have to worry too much about tuning. And in fact, you can get very broad tuning. In this case, I think this was with temperature tuning of the Piplin crystal. So, okay, it's, crystal is 180 degrees. I can't remember how this was tuned, but this must be, I thought it was temperature tunable. This is a temperature tuning device. I mean, but you could also do other things now because now you can combine piplin with intracavity pumping and now make singly resonant oscillators like conventional lasers by putting piplin inside the cavity of lasers, but using very low power lasers. So this is a diode laser pumping a 1 watt diode laser, pumping a solid state laser, neodymium vanadate here, formed between this cavity and this cavity. And now you make a singly resonant OPO between these cavities using piplin. And then you can actually now start seeing that you can get outputs of the order of 70 milliwatts with a 1 watt diode laser with broad tuning made possible by piplin. So now we move from doubly resonant to singly resonant OPO technology. This is also some of the devices that we developed over the years. Again, now the development of periodically poled crystals other than piplin made it possible now to pump also singly resonant oscillators in the green. Because of course, lithium niobate and piplin have got a photorefraction problem. So pumping with high power green is quite challenging, whereas materials such as stoichiometric lithium tantalate can actually be pumped with high power lasers in the green. And now you could generate wavelengths in the visible range using CW OPOs with high powers. You can now make CW laser sources in the visible range. And as I will show you, you can also go to the UV range and so on and so forth. So this is an example. This is using an optically pumped semiconductor laser here, 6 watts at 532 with MGO. This is the OPO cavity. You can actually now see that you can generate over 2 watts. And this is the wavelength tuning of the signal going around 800 in the Ti-sapphire wavelength range. And this is the idler in the infrared. Again, frequency fluctuations of about 60 megahertz. But this is not a locked system. So quite good beam quality considering this was an OPSL with not particularly good performance and good beam quality here. Again, the concepts of dual wavelength generation that I told you about using 2 crystal systems can also be extended to CW SROs now. And again, because of piplin, these SROs, as I said, the thresholds can be much lower and they can afford more loss. So you can actually put all kinds of different things inside the cavity just like a laser. And then we can make 2 crystal dual wavelength OPOs that you can arbitrarily change the spectra all the way by changing the crystal temperature separately and even go to degeneracy. And this is very close. This is the closest we were able to get these 2 wavelengths of about 0.5 terahertz. And this is the stability of the output in the 2 arms. So we can get 2 pairs of signal idler waves that we can arbitrarily tune with very good stability over these hours. You can do other things, broadband generation. I think I will not be able to go much longer. But again, you can use this particular phase matching configurations in piplin. For example, if you use a pump wavelength of 1058, you can see this spectral acceptance bandwidth for parametric process actually for some grating periods and for some wavelengths, pump wavelengths can actually be quite large. So it turns out for this particular grating period that we have 30 microns and we had a fiber laser at 1050 something, at 1030 to 1050 nanometer wavelength. And you can see that basically the phase matching curve can actually become very flat, delta K, which means delta K over delta lambda is about 0. So you can actually have very broad bandwidth. And so this is the parametric gain bandwidth here with a crystal grating of 30 microns, 100 degrees C. So what it means is that because you have a very, very large bandwidth in your acceptance bandwidth, spectral acceptance bandwidth, we can use a very large broadband pump to pump the singly resonant OPO. We resonate the signal, and the signal is narrowband fixed by your optical cavity, but because of, you can then transfer the broadband of your signal, of your pump to the idler while keeping the signal as narrowband. And this is shown here. This is my broadband, this is my gain bandwidth, my spectral acceptance bandwidth. This is the pump laser. This is the depleted pump. This is the input pump spectrum. This is the depleted. And this is what I convert to the idler in the infrared. So you can actually make broadband systems by playing around with all the parameters of your phase matching and using singly resonant oscillators. You cannot actually do this in doubly resonant oscillators because these are going to be confined by your cavity. But in singly resonant oscillators, you can actually do that. And this is the kind of powers and wavelengths. I don't want to, okay, these are some other things to do with CW high power OPOs. Unfortunately, this is a summary table that I've put in here. What I want to also, the last few slides also show you how we have actually gone to shorter wavelengths as well. Using the same generic approaches that we used for femtosecond and picosecond, you can do the same thing with CW singly resonant oscillators, because with the materials and so on, you can now go to all these, with periodic pole materials, you can get sufficiently low thresholds that you can treat these singly resonant CW OPOs as just like lasers. So you can do all kinds of frequency conversion, frequency doubling and mixing inside the cavity without actually the threshold being an obstacle to you doing something useful. And you can now generate very, very high powers. Unfortunately, I don't have time, or fortunately for all of you, I don't have time to cover anything like applications, but I put them in there, and as I said, it's always impossible to cover all the slides that you put in the notes. But they are there for your reference, and there are also, if there is any questions afterwards, I'll be around until tomorrow, so you're very welcome to ask me any questions you like. And I will just relieve you, and thank you for your attention.